Hi everyone, today I'm pleased to present this topic which is more relevant and important in our daily life. I hope you will gain a lot of useful knowledge and better appreciation of this subject. So you can see this is our slide. We are from section 9 and section 10. Our group include 5 persons, which is Yuxian, Dewi, Yojai, Wang Yuehui, and me, Jolashen. So this is our real data survey of this project. So this is the introduction and definition of the problem. Urban flood control challenge under extreme rainfall. So global warming lead to extremely rainfall. Traditional flood control system like drainage, network, manual inspection are difficult to cope with complex water hazard. Our closed space such as tunnel have become disaster area with heightened safety hazard. So with the core issue and impact, main impact is threatening life safety, the causing of economic loss, causing of social costs. So this is the innovation point research that our group do. According to the physical flood control map of the KL Smart Tunnel, this project used digital twin and AI prediction technology to build a full process intelligent and active intervention. The traditional passive response equation has been completely changed and the intelligent upgrading of flood control management has been realized. So next I will pass to my group member.
For this part, I will explain the software architecture of our smart drainage system. The system uses an ESP33 as a main controller. It continuously monitors the water level and makes decisions based on predefined threshold. When the water level reaches certain conditions, the system automatically sends SMS alerts using the GSM module, allowing users to receive warnings in real time. This slide shows the input and output of the system. The main input is the water level sensor, which detects the changes in water height. The output includes a warning LED indicator for visual alerts and SMS notification sent via the SKEE1012 GSM module to inform users remotely when the water level becomes dangerous. The system uses an if-else control logic to determine its operating mode. When the water level is below the low threshold, the system operates in normal mode. When the water level is between the low and high threshold, the system enters alert mode. If the water level exceeds the high threshold, the system switches to flood diversion mode, which indicates an emergency situation. This slide shows the software flow chart of the system. First, the ESP33 reads data from the water level sensor. The reading is then compared with predefined threshold. Based on the comparison, the system switches between different modes. This process runs continuously in a loop to ensure real-time monitoring and fast response.
Good afternoon, my name is Teo-san. I will now continue with the schematic diagram. This schematic consists of several main components: water sensor, jumper wires, a breadboard, ESP32, SIM800L module, a GSM antenna. First, when the ESP32 is powered on, the 3.3V pin acts as our positive supply and is connected to the positive rail of the breadboard. At the same time, the GND pin of the ESP32 is connected to the negative rail of the breadboard, establishing a common ground. The positive and negative pins of the water sensor are then connected to the corresponding positive and negative rails on the breadboard. Next, pin D4 of the ESP32 is connected to the S pin of the water sensor for the power connection. For power supply, the V-in pin of the ESP32 connected to the 5V pin of the SIM800L, while the GND of the SIM800L is connected to the common ground on the breadboard. Moving on to the TXD pin of the ESP32 is connected to the RXD pin of the SIM800L to send common signal from the ESP32 to the SIM800L. Meanwhile, the SIM800L module, the RXD pin of the ESP32 is connected to the TXD pin of the SIM800L to receive feedback signals from the SIM800L. Finally, the GSM antenna is connected to the SIM800L module. With all this connection in place, the circuit setup is complete. That's all for the schematic diagram. I will now pass the presentation to Dewi. Thank you.
I'm Yojai and I'll continue with the hardware part. So the core of our system consists of 3 main hardware components. The first was the NERDS MCU ESP32S. MCU is known as the microcontroller unit and it serves as the central controller equipped with Wi-Fi and easy programming via USB. SIM800L EVB and antenna. It handles cellular communications, enabling SMS alerts over 2G networks. And the water level sensor was provide accurate real-time feedback on water level change. The entire setup is cost-effective with a total cost of 70 ringgit and 38 cents, which means its affordability. Our system offers several notable advantages. It supports real-time local data processing and additionally is low cost and easy to assemble. However, it does have some limitations. The SIM800L module relies on 2G GSM network availability, which may limit coverage in certain areas, potentially affecting the performance of our system. This is our working prototype. Water sensor sends either an analog or digital signals to ESP, which compare the reading against a present safe level. If the level is too high, the ESP32 triggers the SIM800L module, which will SIM card to send an SMS to a store contact. This entire process is automated, allowing for hands-free monitoring and instant alerts.
It's then implemented using Arduino code. The Arduino implementation follows the same if-else structure shown in the pseudocode. Here is a screenshot of the SMS alert sent by our system. So, in summary, the smart drainage system successfully enhances drainage safety and improves response time during high-risk situations. However, the system still has several limitations. The accuracy of the water level reading depends on the sensor quality and calibration. SMS delivery time may vary depending on GSM signal strength. The system currently supports only basic threshold logic and does not include advanced prediction features. So, all of these limitations provide opportunity for improvement in future development.
Let's look at the actual detection of the system. Firstly, there will be an upgrade in accuracy by replacing with high position systems and programs to achieve centimeter level water level monitoring. Secondly, the function functionality will be expanded, adding a water quality module and connecting to meter vector data to automatically open the sluice gates in advance. Finally, a digital integration will be carried out, setting up a cloud platform and developing a lot up to send reminders. These 3 steps will make the system more accurate and intelligent. Now, let's look at the efforts and responsibilities sections. Firstly, there is security assurance with multiple layers of authentication in accordance with international standards. Then there is state governments, including encryption, anonymity, and clear accountability. In terms of public trust, there is transparent communications and listening to the section of everyone. Finally, there is sustainable development, tracing energy saving equipment to reduce environmental impact. These 4 points make the technology both safe and responsible.